Hi, welcome to Socorro's webinar series, Coastal Observing in Your Community. Thank you for sharing your virtual lunch hour with us. My name is Abby Wakely, Socorro's Communications Director, and I will be facilitating and moderating the webinar. Socorro is hosting this webinar series to discuss, highlight, and raise awareness about coastal ocean observing activities in the Southeast U.S. and beyond. Socorro is the regional coastal ocean observing system for North Carolina, South Carolina, Georgia, and Florida. We are one of 11 that make up the NOAA-led U.S. Integrated Ocean Observing System, also known as USIUS. Our mission is to sustain and promote observations that help keep you safe. This is a quick snapshot of the technology we support to accomplish our mission. I want to briefly mention that Socorro has 2 student opportunities open right now. The Vimbu Subramanian Ocean Scholars Award. It is an opportunity to present your research at an in-person or virtual conference, and the Socorro 2021 Data Challenge, where we are asking students to create tools using Socorro buoy or coastal shore station data. Both proposals are due March 12th at 5 p.m., and you can find more information here on our website. All right, let's get to the reason you are all here, the webinar. All participants are in listen-only mode. You are encouraged to type questions for the presenter or technical questions for me in the Q&A box. I will respond to them directly or post the question to our presenter after his presentation. We will not be using video cameras today as we have been experiencing some bandwidth issues, so apologies about that. We are recording this webinar and we'll be posting the recording on the Socorro website. We're very, very excited to welcome Dr. Paul Gator from the University of Florida. He will be presenting the trouble of deep learning. Paul Gator received his PhD in math in 1986. He is a professor and former chair of Computer and Information Science and Engineering and an affiliate professor in Environmental Engineering at the University of Florida. He has been working on artificial intelligence for multidimensional signal and image analysis since 1984 and also has worked with neural networks since 1990. Dr. Gator has processed data from many sensors, including radar, acoustic, seismic, and underwater acoustic, thermal, and multi/hyperspectral sensors. All right, Dr. Gator, thank you so much for joining us. I'm going to go ahead and promote you to presenter so you can share your screen. And you should be getting that opportunity right now.
Okay, can you see it?
Yes, I can.
Excellent. So thank you, Abby, and I'm happy to be here, and perhaps I can kind of convey some of the experiences I've had. One of the things about doing something for a long time is you make a lot of mistakes, and I would like to maybe help people not make those mistakes. So, you know, AI is a big buzzword right now, so there's a picture of my AI device. We've tried to put a brain inside of a computer in a way, but it's definitely artificial. But there are some issues. So let's see. There. Okay. So a lot of times AI things take a look at pictures, and the picture goes into a camera, right? So suppose you had an AI system that was trained to recognize dogs and cats and so on, which actually this is related to. But you show it this particular picture, which I don't think is a dog or a cat, but you never know. The AI thinks this is definitely a picture of a penguin. And you say, no, it is not a penguin. That's when you start pulling your hair out. Okay, so then, you know, our little guy there is quite amazed that this thing could do that. So I'm going to talk about some of the ways that happens and some possible methods for fixing it. Okay, so those are the trouble with deep learning. Okay, everybody knows that AI these days is so big, medical diagnosis, speech, handwriting, natural language, et cetera, et cetera, et cetera. Remote sensing, sensor networks are of great interest, I think, to this group. image processing. So they're very good, and you know, we're making progress. So this is kind of a my very simple illustration of the history of AI. There are really kind of 1, 2, 3, 4 approaches that have come and gone. And I just drew a terrible diagram. This is statistical pattern recognition, symbolic, and here, and this is the one I like. This is the neural network. So in the 50s, 60s, up to 1969, they were really popular, and they came to a dead stop. Until about the mid 80s, nobody did anything. Then in the 90s, they were big again. Then they went dead. Then, now lately, those are the things. Artificial neural networks, ANNs, they are driving the field. So there are really 3 waves of these, you know, where they've gotten better each time. Okay, so what are these things? Okay, so ANNs look like this box in the left. And you have inputs coming in on the left, outputs come in on the right. Inside of this thing, you do lots of multiplying and adding and some exponentials. That's about it. So you have weights, those are the things you multiply by, and then the connections between the different nodes, we call them. Okay. And so deep learning doesn't mean, oh, it's very wise. It just means that there's lots of layers. So instead of like 2 inside layers that you see, there are many layers, 10, 12, something like that. Okay. So that's what deep learning means. It doesn't mean anything else. There have been some astounding accomplishments. So what could possibly go wrong? If you read the popular magazines and everything, it's all the best things since sliced bread. Okay, but not. Okay, and I love this picture. So, you know, here we were in the 1950s and we had the electronic brain. And I like this because, you know, how many arithmetic computations could we do? Not many. Okay, 15,000 a second or a billion in less than 24 hours, which we can now do less than a second. So we've come a long ways. And a lot of what happens is not because of software algorithms, which is bad for me because that's what I do, but it's really about hardware development. Okay, high-speed computers. Oop. Oh, this was one like the first neural network that was out there. And it did character recognition. You see this little setup on the upper left, and then there's the guy that did it, Rosenblatt. Okay, and these things in the lower left, each one of those is a potentiometer, and it's a weight. And these wires over here in the lower right, those are the connections. So of course we can do more than with a cell phone now than they could do then. All right. So again, the basic drivers is every time you get better processors, which means you can implement better algorithms. So you have architectures like GPUs, which are fantastic. You have better memory management, so you can keep the processors going. And of course, as you all know, we have large data sets that you want to process. Okay, what is the problem? The problem is that they learn complicated functions, okay, in high dimensional space. And by high dimensions, it's the it's related to the number of weights in the network, not your input dimension. So you might say, well, I only have 30 measurements, or I have hyperspectral image that only has 50 bands. That's not the problem. The problem is the weights, and they often have millions of dimensions, and they're hard to control, very hard to control. Okay, so, and what happens is these two things, they are not robust. Large changes to inputs can produce absolutely no change in the output, and the opposite can happen. Small changes to input can produce large changes in output. We don't like that. So what we want, this is a new phrase, DARPA's got a program, it's called competency aware. So competency aware artificial neural network can identify when an input is valid or invalid. But if you just train one, use a package, you throw a net in there, you train it, it's almost certainly not going to be good at identifying invalid inputs. So you think, well, if it's invalid, it must be far away from the data set. Why don't we just look at the distance to the training set? We train these things. We teach them how to do these. That's what we do. And teaching a neural network just means estimating the weights, okay, by minimizing some function. That's what training means. Okay, so we represent signals, images, measurements as points in some vector space, and they have many dimensions. So why not just compute distance? This is why. Here's 3D projections of some high-dimensional hyperspectral data that I have worked with. So the one on the left, these were originally, I think, 224 dimensions. I projected them down to 3. So that's what it looks like. These are a bunch of shrubs and things around Santa Barbara, California. This middle one is from a coral reef in Hawaii. So it's actually an airborne sensor that looked down into the coral reef and tried to classify the benthic materials. And this one is from our friendly neighborhood planet Mars. Okay, so I'm showing you these things because this is what you use to train the networks. You show it things like this, only they're high dimensional counterparts. Okay, and then you have to ask yourself, are those points close? Well, I mean, if you look at the middle one, it looks like it could be the average. The red point could be the average of all the blue points, but it's actually not like the training data. And similarly with these others, they look close, but they're not really close. So that's makes it difficult. And I'm showing it to you in 3 dimensions, and we're usually in much higher dimensions than this. Okay, well, let's show you some examples from the literature. Okay, the first one were things I came across back in the 90s. We used to try to read handwritten addresses until they figured out, oh, nobody's going to write handwritten mail anymore. So that was that. Okay, so these are some of the kinds of things that you see. And, if you look at that bottom bar, the image, I think you would have a very hard time reading those correctly. Like the first one, is it TTA, HA? The second one, Q or A, and so on. Most people get maybe one right, maybe two. Okay, so here's some more examples. Y and the 4 are similar, could be a U. It's just a bunch of bumps in that. So we used to have to try to read these, and I used to give this test. What are these? And I'll give this to Abby. So the way to do it, because we didn't know even, if you look at Cowellsville here, where are the characters? We don't even know. So we had to break it up into little pieces, then find the best way to put the pieces together to match city names. Like this is Portland, okay? So we had to try to figure out the best way to match Portland. And what you see is there are many non-characters. In other words, there are many invalid inputs. Okay, here's another look of doing this. I think in the interest of time, I'll go past that. Okay, so in the early days, we built things called self-organizing maps. Okay, this is one of my favorite pictures because this organizes things in high dimensions and gives you a display of them in low dimensions. And you can see, for example, how threes can kind of change to fives. Over here, fives can change to eights, and so on. So it organizes these things, and each one of these little boxes, little images, corresponds to a point in high dimensions. So we can look at the distance between them and ask, does this weird looking thing look like any of these? And then we put them into a classifier. Okay. So we used that same technique with the system that went to Afghanistan and found landmines. This is an array of ground penetrating radars here, and we built an algorithm and implemented it on this thing that used that self-organizing map, and it won a contest of about 15 different entries to become the first algorithm to be implemented on that. And it was the self-organizing map and the robustness to false alarms that made it work. Okay, so here's a bunch of other invalid input examples. So you've seen kind of the natural ones like handwriting, but there are lots of concocted ones, okay? So what is this? Let's look at the concocted ones. These are what you see is an image, and underneath it, you see what a network called them. And this was there are lots of networks that you can just download. They're kind of famous nets, AlexNet and Yolo and things like that. So this was one of those. So you see this pattern here, it called it a robin. And these were high confidence classifications. It called this pattern a cheetah. Here's the one that I had on the first page, king penguin. This one, the blue and the brown one, that's a starfish, and so on. Actually, the remote control is probably the best one. But you can see that these were all high confidence classifications, so they really are not very good at knowing when they don't know. Okay, now there was another paper called The Elephant in the Room. So many of us have heard that phrase, the elephant in the room. So these people took an elephant and put it in a room, in a picture. I won't go into that stuff, that's way too complicated. Okay, so you have this image. This guy's sitting here, I don't know what he's doing. He's got a bunch of stuff. There's a laptop, there's a coffee cup, he's a person, the handbag. So this is just an image, and we ran a network on there, or they did, and it classified all these objects correctly, detected them and classified them. So that's the one you'd see in the press. Wow, look at how good that is. But now they stuck an elephant in here. Here's the elephant. Didn't change anything. Then they moved the elephant over a little bit, and the cup went away. Now the cup's way over here. The cup is right here. The elephant's not near it, but it still made it go away. Here's another one. The elephant now, and it just moved it a little bit. Now it thinks the elephant's a chair, and the chair is a couch, and the cup is still gone. Okay, here's something one of my students did. We have some. We're looking at underwater video and acoustics. So he ran this net called a Yolo net on just a scene of a coral reef out in Hawaii, where we did data collection. And the things inside that blue box were called bird. It was called a bird. That box, the part of the image in that box was called a bird. Okay, I have not seen a bird that looks like that. Okay, so what can we do? We have to fix it. So there are a lot of ways to do it. One thing is you can just have large data sets, and that helps quite a bit, but it doesn't totally resolve the problem. And actually, one of the main points is there's not just one solution to this problem, because there are multiple reasons for it. So you need to use multiple methods to try to mitigate these kind of problems, because you don't want your networks, if you don't want your system to do things like that. Okay, so large data sets can help. Another thing is you can train many networks. Those are called ensembles, and we always train multiple networks, because what happens is every time you train them, what you're doing is solving an optimization problem. You're minimizing some function by changing weights, but the initialization of the weights is random. And the function that you're minimizing has many possible solutions. Some are better than others. It's almost impossible to find the absolute best. So if you train many networks, they'll find different solutions. So these random errors will tend to go away, because one network might make a random error, but 10 networks are very unlikely to make a random error. So if you ever use these networks, ANNs, train more than one, just take them, run them all on the input, and average their outputs, and that will almost certainly be better. The other thing you can do is you can train with outliers. So outliers are just samples of data that don't look like the data you have. And you can do that, and it can help a little bit, but there's no way that you can cover everything. So suppose you're trying to do something that recognize hazardous algae. Okay, so you have some network that's trying to do that, and you say, okay, I want to look at, and you're using, say, a hyperspectral sensor. So you want to look at all of the patterns that are not hazardous algae. Well, that is a lot of patterns, and there's no way you can cover that whole space. So you can't really totally resolve the problem there, but it is helpful. Okay. And the other thing I should say here is that you should also, if you're going to work in an unconstrained environment, like if you're working out in the environment somewhere, you have sensors out in the environment collecting a bunch of data, cameras, all sorts of different things, right? Acoustic sensors, what have you. That's an unconstrained environment. You don't know what's going to happen. There are applications, like, for example, in manufacturing, where that's constrained. So, the cameras on these robots that do the manufacturing, they are unlikely to see anything strange. They know what they're going to see. So most of the inputs are like what they're trained on. But if you're in the environment, if you're in an outside environment, it's almost you have no control over what the inputs are. The other thing that can happen, and I've seen this happen a lot, is sensors go bad. And many of you probably have experience with that too. Sensors go bad. All of a sudden, they start producing strange measurements. So there are ways to take care of it, but it's good. But it's good in those cases. So to actually test on outliers. So it's not enough just to look at the things that are that you're training it to do. Like, you can't just show it hazardous algae. You have to show it lots of outliers, or you can't just show it certain fish classes. So maybe I have a bunch of fish classes. I want to classify fish with underwater video. Well, you know, there may be weird things under there, like an octopus might come around or something, that it hasn't seen. So you have to be able to evaluate its performance not only on the data like it's trained on, but also on data that are potential outliers. And people almost never do that, but it's very important when you're working in an unconstrained environment, like I suspect most of you are. Okay, so what other things can you do? Well, there's a whole class of things that I refer to as keeping it away from bad places. Okay, so these things have lots of equations and things in there, so I'm not going to go through all of that uh, for you, but there's 4 kind of techniques that I'll tell you about. And of course, anybody that's interested in following up, I could even, if you're interested in the details, like I have slides that have the details of these. I just didn't include them in this particular talk. So there are 4 things. One's called an autoencoder. One is called class-dependent projections. Another one is null space avoidance. You want to avoid the null space. Another thing is called self-organizing map, which is kind of a special case of something called manifold learning. Okay, so I don't need that. Okay, so let's look at autoencoders. So what is an autoencoder? So on the left, you see a pattern. It's actually a landmine and a ground penetrating radar. Okay. And it takes that pattern and represents it somehow with this many outputs. So, inputs. So it has turned this image into a set of features, which it could do with convolutions or something like that by extracting features based on your knowledge, those kind of things. And then what it does is it encodes it. The second layer is smaller than the first, and it does all these calculations in here, multiplying and adding and exponentiation, and it gets down to the encoder layer. Then it gets even smaller, and it, it does a bunch of calculations, puts it down there, and finally it gets down to this thing they call the latent variable. And these you can actually think of as features if you want, but that's not how we use it here. So it squeezes the inputs down to a small size, and then it re-expands them again. And the output, you want the output, you try to train it to make the output look like the input. That's why they call it an autoencoder, because it encodes the output, the input, in a way that you can produce it as output. Okay, so one thing about autoencoders is that they learn to reconstruct data well. The training data, the kinds of things you've shown with, but not other data. So outlier data, or maybe not. So one thing you can use them for, I guess I thought I had this here. One thing you can do is build anomaly detectors. So many people use anomaly detectors. For example, if you're doing acoustics, you may want to capture anomalies in acoustics. So you go along and you have some estimate of what the background level looks like. There's a certain kind of noises. Fish are making some noises, waves, and all sorts of noises under there. And you learn the properties of that. There are statistical techniques to do that, where you learn the distribution of them. But this is this one just uses these neural networks. So what you can do is you can take all of these signals from times when there's nothing going on. There is no anomaly, okay? And you can train an auto-encoder to reconstruct that. And what happens then is when you get that background data, like your acoustic data, you put it in the autoencoder, it shrinks it down, then it expands it out. If it's background data, it should get good reconstruction. But if it's anomalous data, so something happened, there's a big sound, or something strange happened, shark came up and all the fish went away, then it will not give you a good reconstruction. And of course, that's only true sometimes, but it's true often enough that this is a useful technique. And then, of course, there are many variations on the theme of how you construct an autoencoder, but this technique works pretty well. Okay, so what does keep away from the bad places? And I had to show you this. This is a hyperspectral image of me in a shortwave infrared, and my student put this together, and she made me look like a Smurf. So I don't know. I like that golden hair though. But anyway, you take input data, and you want to keep away from the bad places and go to the good places. And so you try not to go here, and you try to go here while you're training. Then when you test, when you get new samples, so you've trained a network, takes this input data, and if you get something in your test data that goes in these bad places, sorry, it's probably an outlier. And so you can figure that out. Now, normally you don't just say outlier or not. You say, what's the confidence that this is a valid sample? And you have to deal with that. Okay. Okay. And you can do this kind of good place, bad place thing at every layer in the network. So, and there are many places to do this. Okay. But of course, this is what the mother neural network told all of her children: stay away from the bad places. Here's a bad one. So there's something called the null space. And the null space is strange. So I added, so the thing about the null space is everything that you put into this transformation, like the neural network has a transformation, and in each layer, there's a transformation. So something that goes into a layer, like if you go from the inputs, let's say, let's go backwards. So you have something that goes in the inputs. If it's in a null space of these weights on these connections, then the output will be 0 here. Okay, so if it's in the null space, that's why they call it the null space, it gets mapped to 0. And that happens whenever you go from one layer to a smaller layer. There will be a null space. Okay, so the thing is, it's also additive. So if I take a real sample and I add something from the null space, which is what the thing on the right is, those two get exactly the same output because the null space part just goes to 0. So you have to somehow figure out how to keep the training data away from the null space. And then when you get test data that has some significant relationship to the null space, you want to say, oh, I might want to decrease my confidence that it's a valid input by looking at how much it relates to the null space. Now, it's actually, this one's an active area of research because the null space can also put information in it that's irrelevant. For example, color pictures of dogs. The colors don't help you tell whether or not it's a dog or not, because dogs come in all colors. So the first thing that the network does is throw the color information into the null space. So the null space can be good, but it's also bad. So you have to figure out how to partition it up, and that's what we're doing. Okay, there's our self-organizing map again, because this was our first approach, and it's still a good approach. And for staying away from bad places, because you have to be close to one of these things. Okay, so you see the difference between this and looking at the distance to the training data is here you're saying, okay, I'm going to look at the closest one of all these. If I get an input, and if it's the closest one is far away, then it's far away. I'm far from the training data. Even if I'm in the middle, if I'm in the middle of a circle, I could be close. I'm closer to points on one side than points on the other side are. But, my closest neighbor is far away. Okay, so in summary, the artificial neural networks, even though they have done some amazing things, but you have to be careful because they are not robust. There are several methods for mitigating this problem, and right now we're working on some for both hyperspectral and underwater acoustic data. So we'll have some results soon. And that is the end of my talk.
Great, thanks so much, Paul. If anybody has questions, you can type them into the Q&A box and I will ask Paul. And so, Paul, we do have one question come up from Daniel. Won't a lack of diverse training set cause a larger null space and therefore some reasonable anomalies will begin to the null space?
Well, yeah, a lack of diversity in your training data will it won't necessarily change it could change the size of your null space, but it's not likely to, but it's more likely to leave gaps in your training data so that when you do things like self-organizing map or these things, class-dependent projections, which are very similar, there will be the gaps in the data will cause you to have trouble. So it might actually cause the opposite problem, which is things that are legitimate samples seem bad because they fall into a place where there is a gap in the data. You can also overtrain. But that's a different problem. That's a problem most people know about, overtraining. If you have a lack of diversity in your data set, you can overtrain. So you have too many parameters. You basically memorize the input, the training data, and you don't do well on testing data. But you also can have gaps in your training data that the network may think are not good samples, but they are.
Great, thank you. And we've had a few more questions come in. How to make AI more understandable and less like a black box for domain users? What should we do to promote explainable artificial intelligence?
Yes, that is a very interesting question. And I have a PhD student working on it right now. So one of the first things you have to ask yourself is, who should be able to understand the explanation? Is it just anybody? or does it have to be an expert? So, for example, if your car has a problem, you take it to the shop, and a mechanic can interpret what's going on with your car, and then that mechanic can explain it to you. But most people, especially these days, cannot understand what's wrong with their car. But the mechanic can understand what's wrong with your car. So that's kind of the let's explain it to a network kind of, explain it to an expert approach, which I think, in a sense, is going to be a very good approach because in many cases, uh, so you just have, then you have a human in the loop actually. So if you have some kind of networks running, you can have it produce explanations that somebody who has expertise with that network can understand and then translate to somebody else. And one way that we're doing that is we're looking at uh, paths through that network. So let's see if I can move this thing back. Yeah, I have a network here. So if you look at that network, there you could imagine going from layer to layer in different paths. And those paths can then become uh, different conditions or different scenarios. And you could say, well, what if I have all of these paths? So some paths are not as likely as others. So maybe some paths never occur in your training data, not right? So now you have to look at those paths and you can trace back and say, okay, what are the inputs that are most strongly related to these paths? And then using that, you can come up with a diagnosis. But it's a very active research area right now, and it's always bothered people quite a bit. Another thing that you can do is you can put priors on your input. So, for example, if you're measuring spectra, say in over land hyperspectral images, so you have spectra, there are some spectra that are just not physically possible. I mean, they never ever occur on the planet Earth. So you can put a probability distribution of the kinds of spectra that you believe are possible, and that probability distribution can help you um, to refine. Uh, it can control what happens to the input, and so you can say, okay, if I came outside this probability distribution, there must be a reason. Okay, so, or if I came inside the probability distribution, so I looked like something good, but I wasn't. That's another thing, but it's a very active area of research.
Great, thanks, Dr. Gator. We're getting more questions coming. Artificial intelligence requires big data and supercomputers, but Moore's law will not hold forever. What will have to be done when computer power stops increasing?
Well, the demise of Moore's law has been predicted for many, many years, and of course, it does, it is an effect. Uh, so, one thing that we have to do is we have to do things in parallel. Okay, so instead of trying to cram gates together on a single processor, you have multiple processors, and that helps quite a bit. And most of us have, multi-core uh, desktops or even our laptops now, which are essentially multiple processors our uh, within our central processing unit. So so that's one good thing that's done that can be done. But there will be a limit. But the other thing is managing uh, memory. So how you set up the memory hierarchies to feed things. So one example right now, the best thing to use is a graphics processing unit. And those were actually developed for graphics, but the kinds of calculations that you do in a graphical processing unit are basically matrix times vectors. So there are these adds and multiplies over and over and over again. So you can set them up inside of the chip as a pipeline of processors. Okay, a pipeline of cores, if you will. And so when you go through there, you say you put your first thing in, it does a calculation, then it puts it up, pushes it to the next stage in the pipeline. And when it does that, a new sample comes in. So now you have two things in there. Then this the the first thing that came in, your first pattern, goes to the third part of the pipeline. The one that was in the first part goes to the second, and then there's a new one that comes in. So your pipeline, and actually GPUs work like that. And also then if you're going to feed these pipelines, memory has to be structured so you can keep them full. And a lot of times, way back when I first started, they would have high-speed processors, and they were fantastically fast, but it didn't matter because it took so long to get the data in and out of them that the computation speed was not the problem. So setting up memory hierarchies, cache memories, ways to keep those processors busy is another thing. But those are all, there is a limit to how close you can put wires together, well, they're not really wires, but how close those lines can be in silicon. So I agree, Moore's law is going to get us, but these are the kind of things people are doing now. And the other thing about GPUs is you wouldn't use them to do other things, okay? You wouldn't use them to do accounting. They would be terrible for accounting. So they're specialized processors where the whole architecture of the thing is set up to do a certain kind of calculation.
Great, thank you.
Sure.
We have another question from Robert Weisberg. What are the preferred quantitative metrics used for training? Is preconditioning such as normalization useful?
Normalization is very useful. Absolutely. There's no doubt about it. Normalizing your input can make the difference between even its ability to train or not. So that's another thing. Um, so part of so there are two main kind of objective functions, things that you minimize. One is just the mean square error. So you put patterns in to the network, you're supervising it, so you tell it what you want as an output, and you look at the squared error between the inputs and the outputs, and you try to minimize that, okay? Then you often add regularization terms. So for example, one of the oldest ones is called weight decay, where you also try to minimize the sum of the squares of all of the weights, because the idea, it's called Occam's razor sometimes, the simplest solution is the best. So if you try to minimize the size of your weights, you're essentially using fewer bits to represent a solution. And there are lots of different ways of regularizing these. Now, mean square error is usually good for regression. Like if you're trying to estimate concentrations of, certain chemicals or biological entities, things like that, where the output is not yes or no, but it's like, well, there's 30% or 50%, those kinds of things. But when you're doing pattern classification, there are some others, and gosh, the name is escaping me, right? Cross entropy. There's something called cross entropy, which is used. Um, and and that's usually used more for pattern recognition because it kind of it gives you more of a binary output, a yes or no. Now, there's something else that people do that I would advise strongly against, which is people use what they call the soft max. So when they look at the outputs are usually between 0 and 1, not always, but they take the outputs and they divide them by the sum of all the outputs, okay? And you assume the outputs are positive. You can always make it that way. So you have, say, 3 positive numbers. They're all between 0 and 1. You take their sum and you divide by the sum. You divide each one by the sum. So now they add up to 1. So it's like probabilities. They all represent probabilities. The problem with that in an unconstrained environment is if you get an outlier, since you have these probabilities and they have to sum to 1, it's going to pick something. It has to. It has to say, well, you're basically assuming that everything that comes into this system is exactly like the kind of things I'm supposed to process, and there will not be anything else coming into my system. So I don't like the soft max unless you're in a constrained environment. So unconstrained, constrained are different, but most people that are working in environmental issues, the ocean, is not constrained. So I would not use softmax.
Thank you. Any lessons learned or preferred approaches regarding time series data AI analysis as opposed to AI analysis of single image / raster data?
Yeah, well, that's interesting because we've started doing that quite a bit with the acoustic data. Although I haven't done as much time series, but there are these things called recursive neural networks that can process time series data. So they're basically, in a sense, kind of like linear predictors. So linear predictor, if you have a time series, say you have sample 1, 2, 3, 4, you can predict sample 5 from those 4. And then you shift over, you have samples 2, 3, 4, 5, you predict the next one. Okay. So you can do the same kind of things with these recursive neural nets, and they have a memory. And they do interesting things. I mean, they actually have been developed for initially for kind of language processing, symbolic. So there's a language called the C programming language, and there's a recursive neural net that can produce a C program that has no errors in it, no syntax errors. It won't do anything useful, but all the grammar is correct. So they're very good at that. But you still have the same kind of problems. So, for example, I talked about anomaly detection in underwater acoustics, where you try to learn the background. Okay, that can be done with a time series. So, it's a lot of the same kind of problems. Um, so that you have here, you would have there, because you still have these problems of the outliers. If you have outliers, but often in time series, outliers are kind of anomalies. You also may be looking for trends, in which case you have to calculate some properties. But there's a new kind of network, and I don't know much about it right now, but it's called transformer networks. And they're supposed to be better than all the existing recursive neural networks. And recursive neural networks are generally the way to do time series.
Thanks. We have 5 minutes and 2 more questions, so I think we can get through them. In the example where an image is interpreted as a penguin, do you reply to the AI that they are wrong, then explain what they were looking at and show it a penguin and explain how they are different?
You can take that sample and incorporate it into your training data. So that's kind of the approach that I referred to as training with outliers. So you can say, oh, here's a weird thing that it classified as, here's an invalid input that it classified as a valid input. So I'm going to add it to my training data and keep training. Okay. So you can do that. It's, that's a technique that you can use, and it can help because you'll still keep training it with penguins, but you'll also have that outlier, and then you get another outlier. You say, okay, I'm going to put that in the training data. So over time, it can improve. But the one thing about a lot of these networks is you have to train them with all of the data, all of the time, and when you update them, because otherwise they'll forget. So if you say trained it with a certain data set, and then you started getting new samples over time, if you can't just use the new samples, you have to retrain the whole thing, which is kind of time consuming, because training is very time consuming. Running a network takes no time at all. But so it's a good way to go. We do it. Yes, we do train with as many outliers as we can, and we also test on outliers to make sure we do a good job of rejecting them.
All right, thanks so much. And last question, Dr. Gator. Can we use AI in improving uncertainty representation in models physical stochastic processes? I assume this is where the ensemble AI/machine learning will come in. And how big should the ensemble size be?
Yeah, well, those are two excellent questions. And the first one is, you're absolutely right. Ensembles, there's a paper from way back in the 90s, early 90s, that if you use ensembles, you will reduce the error rate. And so it will affect the uncertainty in your answer. And, I can send you that paper if you're interested. So it definitely does reduce uncertainty. The others, the other methods I've talked about, you can look at measures of uncertainty, but it's still kind of a research area. Whereas with the ensembles, it's pretty well solved. So the other one was how many, and how many is always the $1,000,000 question. If you were Google, you would just do as many as you could. And then you would see where it started to level off in performance. And then you would say, that's the amount. And that's one of the very unfortunate things about these is you don't know. It's the same question as with the hidden units. How many hidden layers? How many hidden units in each layer? There's no analytical solution to those problems.
Awesome, thanks. And I shared your email with Dr. He if he would like to request the paper from you.
Okay.
All right. Seeing that it's 2 minutes to 2, there aren't any time for questions, but we will be sending the recording of this webinar along with the PDF of the slides, if it's okay, Dr. Gator, to everyone who is registered. Perfect. And I want to thank you all so much for attending. It takes about 72 hours for the recording to be processed. And Dr. Gator, thank you so much for the wonderful presentation and the great engaging Q&A session that we just had.
Thank you.